Alright guys, welcome back. So in this video here, we're going to discuss lesson 5.5, which titled the fundamental theorem of calculus, and this is probably the most important, one of the most important theorem in calculus that we discussed in class or any math class that you're going to take or list for math major. So in this theorem allow us to evaluate definite integrals. Okay, so that's what this theorem is saying. So let's go over it. So the theorem is saying that if a function f is continuous function on a closed interval ab. So all this formality here for all class, we don't have to worry so much about this. It's always going to give you a continuous function in all class. But for a regular math class, this condition is really important here. So this is saying that for a given lowercase f is a continuous function on a closed interval ab, and the capital F is any antiderivative of the function f, then we have the following result. It says that the definite integral from a to b of this function f of x, of the lowercase f of x, this definite integral is equal to the capital F function, which is the antiderivative, and evaluate at these endpoints and subtract them. Okay, so they're saying that where capital F of x is any antiderivative. The reason why I said any antiderivative for this to work is because when you evaluate this function f of x, capital F of x at these endpoints, subtract them, the constant c, the plus c then will cancel each other out when you subtract them. So this is saying that to find this in terms of visual, suppose we have a graph of f of x, right, lowercase f of x. Suppose we have a graph of f of x like that, right? So this is our f of x. This saying that if we want to find out the definite integral, if we want to find out the area under f of x between a to b, okay. And in the previous video, we discussed what this means. If we were to find this area, we would have to look at indefinite many small rectangles and take the limit of those, and that would become the exact area itself. So this theorem saying that, hey, there's an easy way for us to do this. If we want to find out this shaded region, this area here, okay, all right, so that right there, a to b, f of x dx. So this definite integral is this area, okay, this area. This theorem saying that, hey, to find this exact area from a to b underneath the curve, all we have to do is find the antiderivative of the function f of x, and evaluate that, right? Plug in b, which is the larger endpoints. So capital F of b subtract capital F of a, and then that should be the answer. Okay, so this result is the same thing as this area. Okay, that's how powerful this theorem is. And it's not hard to do this. It is complicated to do this in the sense of if we have a if we have a complicated function, this, when you find the antiderivative, when we do this, often the result will be a lot fraction, decimal, but you know, we're gonna try to keep the functions nice and easy in this class. But what makes this section a little more difficult than the previous section is there's extra work to be done. After we find the antiderivative, we don't stop there. We go ahead and evaluate the endpoints and subtract them and get the answer, right? So the answer for this lesson in 5.5 different from the 5.2 and 1 is that it's not a function as the answer, it's a value. So this here is just a value, and that value stands for the area. And then we're gonna look at application. How is this area under the curve interpreted differently based on the meaning of the function f of x? If f of x is a cost function, or the marginal cost function, then this area is going to be stand for the total cost. If f of x is the probability function, then this area here, well, if f of x is a function that describes the density of a certain probability function, then the area will be the probability of certain event occur. So there's a lot of application for definite integral. We're gonna look at one of the my favorite in terms of application for this lesson is that the useful life of an asset, right? You have assets in real life, and you know, we want to know when, how long is this asset going to be useful, and is there a mathematical way to describe that? And it turns out there is. And then that so tied to the definite integral concept, so it's pretty cool. So that will be the next couple of videos when we get to it. So in this first video here, I just want to briefly introduce the theorem itself, geometric interpretation of what the theorem is saying, and also not really a proof of the theorem, but also an example that demonstrates how the theorem works, or how we can see how it works. And this is the first example I'm going to introduce here. Not quite the proof, but it's a good example for all class to show what the theorem is saying. Suppose we have a daily cost function for a company in dollars given by this following function. C of x is equal to this here, and then the domain is from 0 to 21. Part A is asked to calculate the change in cost from 0 production to 21 units of production. So this is calculating the total cost from 0 to 21. Part B, we want to graph the marginal cost function, which is C prime of x from 0 to 1, and then calculate that area between 0 to 21 underneath the curve, compare the two results, and see what the connection will be. So let's do it, okay? All right, so calculate the change in cost, okay, from 0 to 21. That's just asking us to find, right, C of 21 minus C of 0. Okay, so let's do that. Okay, so that's going to be -5 times 21 squared plus 210 times 21 plus 400. So that's our C of 21. C of 0, the total cost evaluated at 0 production. So that's just going to be 400, because that's going to be fixed cost. If you plug 0 there, 0 there, you're going to get just 400. Okay, so let's go ahead and do that. If we do the math correctly, if I punch this into my calculator, I'm going to get the total change in cost is going to be $2,205. Okay, so that's going to be the total change in cost. Okay, part B is asking for graph the marginal cost function from 0 to 21. So let's go ahead and find the marginal cost function first. So that's just C prime. So that's going to be -10x plus 210. Okay, so that is a marginal cost. Let's graph this. Okay, and then we want to graph it from 0 to 21 for x. Okay, so let's go ahead and do that. Okay, all right. So this is x. All right. Let's see, when x is 0, our C prime of x is going to be 210, so that's going to be that. When x is 21, let's say this is 21, then let's see, that's going to be 0 for y. Okay, so here's our graph, right? It's going to have a decreased slope from that to that. Okay, so this is the function C prime of x, which is the marginal cost, right? So this is the marginal cost there. Marginal cost functions. Okay. The second part of this here is to calculate the area from 0. The calculate area between 0 to 21, or find this area. Okay, so this is what it's asking. Okay, so what is that area? What is the area under the curve from or between x equals 0 to 21. Now suppose we don't know anything about definite integral, we don't know anything about antiderivative yet. How will we calculate this shaded area? Well, that shaded area looks like a rectangle. We know how to find an area of rectangle. So it is just an area of a, excuse me, I said triangle, not rectangle. Okay. Well, how do we find area of a triangle? It's going to be area equal base times height divided by 2. Okay, so that's going to be, our base is 21. Our height is going to be 210 divided by 2. What would that be? Well, let's see here. So that's just going to be the same answer as what we got above, 2,205. So what did we just show? Part C, compare the results. Okay, so what did we just did? We graph the marginal cost, which is the derivative of total cost function, and find that area without using the antiderivative. Just you know, use good old triangle area formula. That area is equal to, okay, so we say that say that the answer in part B is the same as part A. Okay. Well, part B is the total area under the curve. We did that by using the formula. Part A is just calculating the total change in cost from the 2 points. Okay. How do we put this together? Now notice that if we find the antiderivative of c prime of x, which is the marginal cost there. So if we find the antiderivative, well, c prime of x, the antiderivative of c prime of x, which is going to be capital C of x. Okay. And then if we evaluate that from 0 to 21, this is just saying that, hey, what is c of 21 minus c of 0? Well, that itself now equal to the area under c prime of x from 0 to 21. Okay, so hopefully that makes sense what we just did there, right? We calculate the two different things, okay? One is the change in cost from one production to another level of production, and then one is the area underneath another function, and this function is a marginal cost function, which happens to be the derivative of c of x itself. And it turns out both answers are the same. Well, that's what the fundamental theorem is saying. Given a definite integral, okay, if we want to find out what would be that definite integral between two limits a and b, then we just find the antiderivative and evaluate at the endpoint, subtract them, and then we got the answer. So just a little more, just a bit of information. So this is called the lower limit of integration, and then this is called the upper limit of integration. Okay, and then recall this is the integrand function. Okay, all right. Okay, so in the next video, I'm gonna go over several more examples, just math example before we get to application. How to apply the fundamental theorem of calculus. How do we know when to use it based on the instructions, and you know, do the math and then get the answer. So